Hello, I'm Seema and welcome to part 4 of the topic Acids and Bases in Organic Chemistry. In this video, I'm going to continue with our discussion of the use of the mnemonic CARIO in order to compare the acidic and basic strengths of organic acids. In the previous videos, we discussed how we use charge to compare the acidic and basic strengths. And then we moved on to the atom which bears the charge. Now, today I will discuss R, that is resonance, the third step. I've used 3 examples to explain this step to you. The first one is that we are now going to compare ethanol and ethanoic acid. And we are going to see which one of these should be a stronger acid. So the first step should be to write down the equations of deprotonation and to get the conjugate base. I have already done that. This is ethanol, and ethanol on deprotonation gives me the ethoxide ion, and this is ethanoic acid, which on deprotonation gives me the acetate ion. Now, or the ethanoate. Now that we have these, the first step is charge. We notice that both of them have a charge of -1. Therefore, we cannot compare the acidic strength on the basis of charge. So we move on to the next step, that is the atom bearing the charge. And we notice that both of them have oxygen, which is bearing the charge. If they were different atoms, we would have considered, or different elements, we would have thought about the periods to which they belong, or the group, if they belong to the same group or the same period. And if not, we would like to try and follow certain trends and judge their acidic character. But since both of them are oxygen, this step also we cannot compare them on the basis of the atom bearing the charge. So we now come to the third step, which is resonance. What is resonance? You know, when an organic molecule has alternating double bonds, the electrons of the second bond, they have a tendency to get delocalized. And when they get delocalized, delocalization means they are not fixed between 2 atoms. And when there are alternating double bonds, that is a single bond, a double bond, a single bond, a double bond. When they have alternating single and double bonds, these electrons of the second bond are called pi electrons. These pi electrons have a tendency to move on to the next single bond. And when this happens, since these are carbon atoms and carbon cannot form 5 bonds, therefore this carbon here, if it has a double bond, the electrons of the second bond, this second bond may move here, but the pi electrons of the next double bond, they move on to the next carbon. So this delocalization or this movement is known as resonance. And sometimes when you have electrons, lone pairs of electrons which are also present in conjugation with these double bonds, these lone pairs also participate they also can be delocalized and they also participate in resonance. That was just about resonance. And resonance imparts stability to the structure, right? Resonance gives stability to the structure. So we notice that here there is no double bond. For resonance to happen, there should be a double bond. Remember, there should be alternating double bonds, and we call that conjugation. So here there is no possibility of resonance. Therefore, this ethoxide ion, whatever, it has a negative charge over the oxygen. But when we look at acetate ion, we find that there is resonance possible in the case of acetate ion. A lone pair of electrons present here, I've already made these arrows, can move to the next single bond. And when this happens, this carbon will now have 5 bonds, and carbon is not allowed to have 5 bonds. And therefore, one of these bonds, the pi electrons of this bond, it moves up to the oxygen adjacent to it. And therefore, the negative charge which was present here, with 2 electrons moving here, the negative charge is lost. But 2 electrons which move up to this oxygen, that causes the negative charge to move from this oxygen to the next oxygen. Let me just make the resonance structures to explain this to you. This is the original structure that we have: oxygen, double bond, and this is the oxygen, having 1, 2, 3, 4, 5, 6 electrons. And the negative charge is on this oxygen. A lone pair here moves here, and one of the pi pair of electrons, the pi bond, it moves to this oxygen. This already had 1, 2, 3, 4 electrons and it was neutral because it has 8 electrons in all. So it forms the resonating structure, and the resultant structure of this would be oxygen now has 1, 2, 3, 4 electrons, and this pair of electrons has formed a bond here, and the two double bond here forms a single bond because 2 electrons have moved up to this oxygen, now giving it 6 electrons, and the negative charge comes up to this oxygen. So now these two resonating structures, whenever you have resonance in a molecule, it imparts more stability, which means that the acetate, all other factors are the same. The acetate ion should be more stable in comparison to the ethoxide ion because acetate ion shows resonance, right? So that is the first thing that you should know, that a molecule which shows resonance will be more stable than a molecule which does not show resonance, right? So when we are comparing these, we say the acetate ion, due to the presence of resonance, should be more stable. And if this is more stable, this is less stable. If this is less stable, what does it tell me about the basic character? Less stable means it is more reactive. So it is a stronger base. The ethoxide ion would be a stronger base, while the acetate ion would be a weaker base. And what does it say about the acids then? The less stable one would be a weaker acid, would be from a weaker acid, and the more stable conjugate base would be from a stronger acid. So on the basis of this, we know, or we could say that a stronger acid gives rise to a weaker conjugate base, and a weaker acid would give rise to a stronger conjugate base. So from this we understand, out of this pair, which is the stronger acid? Acetic acid should be stronger than ethanol because of the presence of resonance. Let us now move on to the next example. We have cyclohexanol and we have phenol. Now I have chosen an example where both the compounds show resonance, right? Both of them show resonance. So now how are you going to compare which one is more stable and which one is less stable? In order to understand that, let us first form the conjugate bases and then look at their resonance structures. This is cyclohexanol, which means there is a double bond, just one double bond in the cyclohexane ring. So that's what makes it cyclohexene. And all means this oxygen has lone pairs of electrons. So on deprotonation, this hydrogen is removed, so the charge comes on the oxygen, and this is the conjugate base that we obtain. So the conjugate base will show resonance. One lone pair of electrons can move from here to here, right? And as soon as this happens, the carbon has 5 bonds which it is not allowed to make. Therefore, the pi electrons of this double bond, they move to the next, they shift to the next carbon. They are pushed away to the next carbon. So it gives rise to a resonating structure, and the structure would be now the oxygen has formed a double bond here. Instead of 6 electrons, there are only 4 electrons because 2 of those electrons have been used up to make the double bond. The double bond here has been pushed to this carbon, therefore the lone pair of electrons would now be present on this carbon, and hence the negative charge now moves from oxygen to the carbon of the ring. Is it possible to make more, for any more resonance to be there? No. Only these two structures are possible. If this electron has to move, it needs a conjugate double bond, that is an alternate double bond. So for it to show resonance, it will have to move back to form the double bond. The double bond here would have to move back to give the negative charge or the lone pair of electrons to oxygen, thereby giving the negative charge to oxygen back to it. So these structures, they resonate between each other, right? So we find that cyclohexanol shows resonance, but it has 2 resonating structures. Also, the resonance, when it is between, there is a difference between the negative charge being on oxygen and the negative charge being on carbon. that resonating structure in which the negative charge is on the more electronegative atom would be more stable. Why? Because an electronegative atom has a tendency to pull the electrons towards itself. It has a stronger attraction for the electrons. So obviously, when the electrons go on the oxygen atom, it would be more stable. But when the electrons are on carbon, carbon is not so electronegative. It doesn't really want the electrons. So you're pushing the electrons on it. So this structure would not be as stable as this one. Right? So now let us come to the next compound, that is phenol. Phenol also has 3 alternating double bonds and there is a lone pair of electrons on oxygen. So it would show much more resonating structures. So let us see what its resonating structures are. Let us first make the original molecule. Now we have oxygen having 1, 2, 3, 4, 5, 6 and the negative charges here and the double bonds are here. Now one pair of electrons from here moves and forms, shifts here. And as soon as it does that, this carbon now has 5 bonds and that would not be stable. Therefore, the pi electrons of this bond should move to are pushed to the next carbon atom, thereby resulting in the next resonating structure. So the next resonating structure is here. Now oxygen has a double bond with oxygen and only 4 electrons, and the negative charge, no negative charge, because as soon as it loses those 2 electrons and it pushes it to the bond, the negative charge moves away. Now the pi electrons which were present here, they move on to this carbon and therefore the lone pair of electrons comes here and the negative charge comes on this carbon, while the other 2 bonds remain where they are. Right? Now what happens when there is negative charge here and the lone pair of electrons? This lone pair is pushed on to the next bond to participate in resonance. So this lone pair now moves here, but as soon as it does that, this carbon now has 5 bonds. And since it has 5 bonds, it cannot have 5 bonds. The pi electrons of this bond will move on to the next carbon. Therefore, from this we obtain the next resonating structure. And what is the structure? We have oxygen having 1, 2, 3, 4 electrons. This pair has formed a double bond here. And the double bond here has moved and the lone pair now comes to this carbon. So the negative charge also comes to this carbon while this bond remains where it is. Now, in the next step, the lone pair will move on to the next double bond. So this lone pair now shifts here, and as soon as it shifts here, this carbon has 5 bonds, which it cannot have. So it will move the pi electrons to the next carbon. This will result in the formation of the next resonating structure, which would be a double bond here, here, and now these two electrons will form a double bond here, and the electrons of this double bond will move here and the lone pair would now be present on this carbon, thereby giving it a negative charge. Right? Now, this can again move to the next single bond, making it a double bond. And that would result in the electrons of the double bond, sorry, there should be 4 electrons here. The pi electrons of the double bond with oxygen to go back to oxygen, thereby bringing back the negative charge to oxygen, which would be nothing but our first structure. Right? Only the bonds have been shifted. So you could make it as one of the resonance structures. So the next structure you could say would be where this oxygen gets back the 6 electrons, the negative charge comes back to this oxygen, these bonds are already here, and this is the double bond that has been, the new bond that has been formed. Right? So we find that phenol formed many more resonating structures. And the more the resonance, or the more the resonating structures, more is the stability. So out of these two compounds, that is cyclohexanol and phenol, which one should be more stable? The phenoxide ion should be more stable. If this is more stable, this is more acidic, or this is the stronger acid, and this is the weaker acid, and this is the stronger base, conjugate base, and this is the weaker conjugate base, right? So that is the stronger conjugate base. It is less stable and it is less stable. Now we have noticed an example where we had no resonance, two resonance. So the compound which had resonance was more stable, formed a more stable conjugate base, and therefore was more acidic, was the stronger acid. And out of these two, where we saw resonance in both the molecules, the one which shows more resonating structures was more stable. Now we come to a third kind of an example. And what is that? That you have acetic stronger, that is acetic acid, ethanoic acid, and now we want to compare ethanoic acid to phenol. Right? Let us now compare ethanoic acid to phenol. This would be very interesting. Now, if we are comparing ethanoic acid to phenol, both of them have single negative charge, both of them have the negative charge on oxygen, but there's a difference now. In ethanoic acid, the conjugation or the resonance is where the negative charge is shuffling between two oxygen atoms. While in phenol, there is only one structure where you have the negative charge on oxygen. In all other structures, the negative charge is with the carbons of the ring. And carbon, I told you, is less electronegative. And since carbon is less electronegative, out of all these structures, which one do you think would be more stable? The one where the negative charge is on oxygen would be more stable. But the structures where the negative charge is on the carbons would be less stable. In this case, this is actually the same structure if you really see. So in this case, the resonance that you see is between two oxygen atoms, So if you have, if you imagine electronegativity to be something like a weightlifter being able to hold weights. Now, both these weightlifters, both the oxygens are strong weightlifters, so they can hold the weights better. So when the negative charge is shuffling between these two, they will be more stable. But here, the weightlifter, you have only one strong weightlifter. The other weightlifters are carbons who are weak. They cannot hold the weights well on them. So the negative charge is shuffling between the less electronegative atom. So although phenol appears to have a larger number of resonating structures, yet phenol is not as strong an acid as ethanoic acid. Why? Because although it shows only two resonating structures, these resonating structures are more stable because of the presence of a more electronegative atom on oxygen. Right? Interesting, isn't it? So these were the first three steps of CARIO, that is the charge, the atom bearing the charge, and resonance. In the next video, we are going to see inductive effect. If you found this video helpful, please give it a thumbs up, subscribe to my channel, and recommend it to your friends, and please keep returning for more videos in chemistry. Thank you. Bye-bye.